Okay, I want to describe how the cochlea creates labeled lines for frequency. Okay, so one consequence of breaking the sound wave up into simpler components is the systematic representation of sound frequency along the length of the cochlea. Okay, so there's an organized manner in which frequency is represented along the length of the cochlea. Okay, so that's one thing I want you to understand. This is an important organizational feature as well, and it's preserved throughout the central auditory pathway. So it's an important organizational feature, hence it's preserved throughout the central auditory pathway. Okay, so how does this process work and what does it achieve for us? So at any given point along the length of the cochlea, there are hair cells. In a previous video on transduction, in the cochlea, I talked about hair cells, and I talked about how they're activated, and I talked about what causes these depolarizations. I talked about potassium ion channels, mechanically gated potassium ion channels, and also voltage gated calcium channels that lead to this change in membrane potential. Anyway, at any given point in the length of the cochlea, there are these hair cells, and they're activated in response to a specific frequency. So each hair cell sort of has its own frequency. There's this frequency that it responds best to. So each cell creates a labeled line. Okay, each individual hair cell creates a labeled line that only responds to the particular frequency it's been assigned, essentially. So it only responds to 300 hertz. Okay, so when you hear something that's at that 300 hertz level, it responds. Okay, this hair cell is activated. So the intensity of the sound can be determined. So the intensity of the sound can then be determined from this arrangement by looking at the number of individual nerve fibers that are activated in response to the sound at that frequency. Okay, so essentially you just want to look at how many nerve fibers are being stimulated, and if there's a large number of them, then you know that the sound is intense. If there's not as many, well, you know it's not as intense. Pretty much as simple as that. And the more fibers activated, the more intense the sound is. And particularly for humans, as an example, the hair cells around the 300 hertz range, okay, so around this 3, or maybe I actually should have said 3,000, excuse me, this is 3,000 hertz range. So anyway, the hair cells around the 3,000 hertz range are more sensitive and have a lower threshold, okay, and the reason for that is that that's where most human speech occurs, okay, that's the level at which most human speech is occurring at, so the frequency rather, that most human speech is occurring at. So it's no surprise that evolutionarily we developed to hear much more sensitive in the area in which other people were talking. So it's very important, if you think about it in terms of evolution, that this communication process, they think communication, the ability to communicate, might have been one of the reasons that modern humans evolved. So you can see that this is important, it's evolutionarily left over, but more importantly, there are specific hair cells, okay, that are stimulated in this 3,000 hertz range. And they create this sort of labeled line. Each individual hair cell creates this sort of labeled line for a specific frequency.